the concept of inertial frames of reference stands as a cornerstone of astronomical observation, calculation, and theory. These reference frames provide the fundamental coordinate systems through which we describe and predict the motion of celestial bodies, from nearby satellites to distant galaxies. At their core, inertial frames are those in which objects remain at rest or move with constant velocity unless acted upon by an external force, following Newton's first law of motion. This principle enables astronomers to develop consistent mathematical models of cosmic phenomena, accurately track celestial objects, and navigate spacecraft through the solar system and beyond. Without properly defined inertial reference frames, our understanding of the universe would be fundamentally incomplete. A reference frame, in its most basic form, is a set of coordinates used to record the position and time of events. These coordinate systems provide the necessary structure for measuring and describing the locations and movements of objects in space. In astronomical contexts, reference frames allow observers to quantify distances, angles, velocities, and accelerations of celestial bodies. They serve as the essential foundation upon which astronomical calculations and observations are built, enabling everything from simple stargazing to complex orbital predictions. Reference frames can be broadly classified into two primary categories: inertial and non-inertial. An inertial reference frame is one that is not accelerating, including rotation. In such frames, objects follow Newton's first law of motion, maintaining constant velocity unless acted upon by external forces. The laws of physics take their simplest form in inertial reference frames, without the need to introduce additional terms to account for the motion of the frame itself. This simplicity makes inertial frames particularly valuable for astronomical calculations and theoretical work. Non-inertial reference frames, by contrast, are accelerating, which introduces complications in the description of motion. In these frames, objects appear to experience fictitious forces that arise not from physical interactions, but from the acceleration of the reference frame itself. Common examples include the centrifugal force and Coriolis force, which become apparent in rotating reference frames. These fictitious forces add complexity to the mathematical description of motion and can obscure the underlying physical principles at work. The mathematical description of reference frames in astronomy typically involves Cartesian coordinate systems with three spatial dimensions, x, y, z, and time as a fourth dimension. More sophisticated treatments may employ spherical coordinates, particularly useful for describing positions on celestial spheres, or cylindrical coordinates, which are advantageous for systems with axial symmetry like spiral galaxies. The transformation between different reference frames is achieved through well-defined mathematical operations that preserve the underlying physical laws. In Newtonian mechanics, the transformation between inertial reference frames follows the Galilean transformation, expressed as r, jar r0, vt, t, jars t, t0, where r and t are the position and time in the new frame. R and t are the position and time in the original frame. R0 and t0 are the shifts in the origin, and v is the relative velocity between the frames. Under this transformation, time intervals remain invariant, and distances between simultaneous events are preserved. This mathematical framework has proven remarkably effective for most astronomical applications, despite its limitations at very high velocities. The concept of inertial reference frames has deep historical roots, tracing back to the work of Galileo Galilei and Isaac Newton. Newton's formulation posited the existence of absolute space and time, with absolute space serving as a fixed, immovable backdrop against which all motion occurs. According to Newton, an inertial frame was one that moved with uniform translation relative to this absolute space. This conceptualization provided a powerful framework for understanding motion, though it also raised philosophical questions about the nature of space itself. Newton's laws of motion take their simplest form in inertial reference frames. The first law, in particular, can be viewed as defining the characteristics of an inertial frame. A body at rest remains at rest, and a body in motion remains in motion with constant velocity unless acted upon by an external force. This elegant simplicity in the description of physical phenomena is what makes inertial frames so valuable in astronomy and physics more broadly. The concept of inertial frames evolved significantly in the late 19th century, largely through the work of Ludwig Lange, who coined the term inertial frame of reference in 1885. Lange sought to replace Newton's abstract notion of absolute space with a more operational definition based on observable phenomena. He defined an inertial frame as one in which a mass point thrown from the same position in three different, non-coplanar directions follows rectilinear paths each time. This operational approach shifted the focus from philosophical questions about absolute space to practical considerations about how reference frames can be established and utilized in scientific inquiry. The Galilean principle of relativity, which predates Newton's work, states that the laws of mechanics have the same form in all inertial frames. This principle recognizes that there is no preferred inertial frame. All inertial frames are equivalent for formulating physical laws. In astronomical terms, this means that the same laws that govern the motion of objects on Earth also apply to celestial bodies throughout the universe. This universality of physical laws across inertial frames forms a foundational principle of modern astronomy. In practical astronomy, truly inertial reference frames are theoretical idealizations rather than perfectly achievable realities. Astronomers must approximate inertial frames using observable celestial objects. Historically, the fixed stars were considered to provide a good approximation of an inertial frame, as they appeared to maintain the same relative positions over human timescales. These distant stars, being so far away that their proper motions are nearly imperceptible from Earth, served as convenient reference points for astronomical observations and calculations for centuries. Modern astronomy has refined this approach, recognizing that even the fixed stars are in motion. Our Sun orbits the center of the Milky Way galaxy, as do other stars, and galaxies themselves move relative to one another. However, for many astronomical applications, especially those covering relatively short time spans, days to years, the assumption that the distant stars represent an inertial frame remains a reasonable approximation. This practical compromise allows astronomers to establish reliable coordinate systems for tracking celestial motion. As astronomical measurement precision has improved, more sophisticated celestial reference systems have been developed. These systems typically define a coordinate origin, such as the solar system barycenter or the Earth's center, coordinate axes often aligned with the celestial equator and ecliptic, and a timescale such as terrestrial time or barycentric dynamical time. The International Celestial Reference Frame, established in 1998 and refined several times since, represents the current standard for high-precision astronomy. Rather than using stars, which have measurable proper motions, the ICRF is based on the positions of distant extragalactic radio sources, primarily quasars and active galactic nuclei, whose extreme distances make their angular motions negligible from Earth's perspective. The precision of these reference systems continues to improve with advances in observational technology and analytical techniques. Modern astrometric missions like Gaia, capable of measuring stellar positions with unprecedented accuracy, are refining our understanding of stellar motions and improving the precision of celestial reference frames. These increasingly accurate reference systems enable new discoveries and more precise predictions in all areas of astronomy, from solar system dynamics to cosmological studies. Earth's surface does not constitute an inertial reference frame due to two primary factors: the planet's rotation on its axis and its orbital motion around the Sun. The Earth's rotation introduces the Coriolis effect, which deflects moving objects relative to the Earth's surface. The centrifugal force, another consequence of rotation, slightly reduces the effect of gravity at the equator compared to the poles. These effects clearly demonstrate the non-inertial nature of Earth-fixed reference frames. Despite these limitations, Earth-based reference frames remain valuable for many astronomical purposes. For observations covering short time periods or requiring moderate precision, the non-inertial effects can be calculated and corrected. Various Earth-centered reference frames have been developed for different applications, including Earth-centered Earth-fixed coordinates, which rotate with the Earth, and Earth-centered inertial coordinates, which maintain fixed directions in space. The transformation between these frames involves complex calculations accounting for Earth's rotation, precession, nutation, and polar motion. Space-based platforms offer significant advantages for establishing reference frames that more closely approximate inertial conditions. Satellites orbiting Earth can minimize the effects of Earth's rotation, while spacecraft at the Sun-Earth Lagrange points or in heliocentric orbits can reduce the influences of both Earth's rotation and orbital motion. These platforms enable more precise astronomical measurements, free from atmospheric distortions, and with reduced systematic errors related to non-inertial effects. Space telescopes such as Hubble, Gaia, and James Webb exploit these advantages to achieve unprecedented accuracy in astronomical observations. The Gaia mission, in particular, has revolutionized astrometry by measuring the positions, distances, and motions of over 1 billion stars with exceptional precision. These measurements have dramatically improved our understanding of the Milky Way's structure and evolution while providing a more accurate reference frame for other astronomical observations. Orbital mechanics represents one of the most direct applications of inertial reference frames in astronomy. The calculation of orbital trajectories, whether for natural satellites like moons or artificial satellites like spacecraft, relies fundamentally on the principles of motion in inertial frames. In orbital mechanics, inertial reference frames are typically defined with respect to the fixed stars, providing a stable coordinate system for describing and predicting orbital motion. The equations of orbital motion, from Kepler's laws to the more general formulations based on Newton's laws of motion and gravitation, are formulated in inertial reference frames. These equations allow astronomers and aerospace engineers to calculate precise orbital elements, predict future positions, plan spacecraft maneuvers, and understand the long-term evolution of orbital systems. The success of satellite deployments, interplanetary missions, and space-based observatories depends critically on accurate calculations within appropriate reference frames. Spacecraft navigation through the solar system presents some of the most demanding applications of inertial reference frames. Interplanetary missions require extraordinary precision in trajectory planning and execution, with course corrections calculated to sub-meter accuracy over distances of millions or billions of kilometers. Inertial reference frames provide the necessary coordinate systems for these complex calculations, enabling achievements like the Voyager mission's grand tour of the outer planets, the Cassini probe's exploration of Saturn, and the New Horizons flyby of Pluto. Satellite operations in Earth orbit also rely heavily on inertial reference frames. Communication satellites must maintain precise orbital positions and orientations, while Earth observation satellites require accurate knowledge of their positions to properly interpret their measurements. Satellite constellations like GPS depend on precisely synchronized orbits, with their operation requiring corrections for both special and general relativistic effects due to their velocity and position in Earth's gravitational field. These applications highlight the practical importance of inertial reference frames in modern space technology. Einstein's theory of special relativity fundamentally transformed our understanding of inertial reference frames. According to the principle of special relativity, all physical laws, not just Newton's laws of motion, take the same form in all inertial frames, and no inertial frame is privileged over another. This principle eliminates the need for absolute space as conceived by Newton, and establishes the equivalence of all inertial frames, regardless of their relative velocity. A key insight from special relativity is that measurements of space and time are not absolute, but depend on the relative motion between reference frames. The Lorentz transformations, which replace the Galilean transformations of Newtonian mechanics, describe how coordinates transform between inertial frames moving at constant velocity relative to each other. These transformations preserve the speed of light as a universal constant in all inertial frames, leading to effects such as length contraction and time dilation that become significant at velocities approaching the speed of light. General relativity extends the concept of inertial frames to account for gravity's effects on space-time. According to Einstein's equivalence principle, the effects of gravity are indistinguishable from those of acceleration, implying that gravitational fields can be viewed as manifestations of curved spacetime. In this framework, freely falling bodies follow geodesics, the equivalent of straight lines in curved spacetime. This perspective reframes our understanding of orbital motion. Planets orbit the Sun not because of a force acting at a distance, but because they follow the curved spacetime created by the Sun's mass. In astronomical context, general relativity predicts several observable effects that have been confirmed through precise measurements. These include the precession of Mercury's orbit, the deflection of light by the Sun's gravitational field, gravitational redshift, and gravitational time dilation. Modern precision astronomy must account for these relativistic effects to achieve accurate results. For example, the Global Positioning System, GPS, includes corrections for both special relativistic effects due to satellite velocity and general relativistic effects due to the difference in gravitational potential between the satellites and Earth's surface to maintain its meter-level positioning accuracy. The International Celestial Reference Frame, ICRF, represents the state-of-the-art in astronomical reference systems. Established by the International Astronomical Union, the ICRF is based on the positions of extragalactic radio sources observed using Very Long Baseline Interferometry, VLBI. These sources, primarily quasars and active galactic nuclei at vast distances from Earth, show negligible proper motions due to their extreme remoteness, making them excellent markers for a stable reference frame. The ICRF achieves sub-milliarc-second positional accuracy, providing a quasi-inertial reference frame for high-precision astronomy. The Solar System barycentric frame, centered on the center of mass of the Solar System rather than the Sun itself, provides an important reference frame for planetary and spacecraft dynamics. This frame accounts for the gravitational interactions among all Solar System bodies, recognizing that even the Sun moves slightly in response to the gravitational pulls of the planets, particularly Jupiter and Saturn. Ephemerides, tables of predicted positions of celestial bodies, are often calculated in the barycentric frame to provide the highest accuracy for astronomical predictions and spacecraft navigation. Various specialized reference frames have been developed for specific astronomical applications. The galactic reference frame, centered on the Milky Way's center with its principal plane aligned with the galactic disk, offers a natural coordinate system for studying galactic structure and dynamics. Heliocentric ecliptic coordinates are useful for solar system studies, while topocentric coordinates, centered on the observer's location on Earth, are convenient for planning observations. Each of these specialized frames serves particular purposes in astronomical research, with well-defined transformations allowing conversion between different systems as needed. The development and maintenance of these reference systems require international collaboration and continuous refinement. Organizations such as the International Astronomical Union, IAU, establish standards and coordinate efforts to improve reference frames through new observations and analytical techniques. The evolution of astronomical reference frames reflects advances in observational capabilities, computational methods, and theoretical understanding. Future reference frames may incorporate new classes of extragalactic sources, take advantage of space-based astrometric missions with unprecedented precision, or extend to include reference points throughout the local group of galaxies. Inertial frames of reference form the conceptual foundation upon which our understanding of celestial mechanics and astronomical phenomena is built. From Newton's initial conception of absolute space to modern relativistic frameworks, these reference frames have evolved to accommodate increasingly precise observations and more comprehensive theoretical models. The practical approximation of inertial frames in astronomy, using distant stars and extragalactic sources, enables consistent measurements and predictions that span the cosmic scale from Earth-orbiting satellites to the most distant observable galaxies. The distinction between inertial and non-inertial reference frames remains central to astronomical practice. Earth-based reference frames, while convenient for many purposes, must account for non-inertial effects due to Earth's rotation and orbital motion. Space-based platforms offer closer approximations to ideal inertial conditions, enabling more precise measurements free from terrestrial complications. The interplay between these different reference systems, connected through well-defined coordinate transformations, creates a coherent framework for astronomical research that spans observational techniques, time periods, and spatial scales. The applications of inertial reference frames in astronomy extend from practical concerns of spacecraft navigation and satellite tracking to fundamental questions about the nature of space, time, and gravity. Relativistic considerations have deepened our understanding of reference frames, revealing the intimate connection between gravity and space-time geometry. As observational technologies continue to advance, enabling ever more precise measurements of celestial positions and motions, our implementation of inertial reference frames will undoubtedly evolve. These reference frames will remain at the heart of our efforts to understand the universe's fundamental nature and the complex motions of the celestial bodies within it.